Okay, we're going to talk about the first main theorem of this course, which is the fundamental theorem of line integrals. And it's, I would say, the first version of the fundamental theorem of calculus in 2 dimensions and 3 dimensions and so on. So let me just state what it looks like. It says that if you have a gradient line integral over some curve, it's actually equal to the endpoints, where the curve starts at A and ends at B. So remember that the 1D version of this is that if your curve is not just a line segment on the real line, then the integral of f prime of x dx is f of b minus f of a. So really, all we're doing here is we're vectorizing the points, and we're vectorizing dx, and we're vectorizing the derivative of f. And we're putting vectors here because we're now in higher dimensions. That's really the only essential difference. So let me try to explain where this formula comes from. So in 1D, you could think about this expression here as df. Okay? Because remember, if we have a u substitution, u equals, say, x squared, then du, we did 2x dx, right? That's why this f prime of x dx, you can call this df. So this is really just the integral from f of a to f of b of df. Okay, so then clearly these things are equal. That's one way of thinking about the fundamental theorem of calculus. Well, in higher dimensions, what we're really doing is we're saying that the gradient of f times dr is also df. But now it's just because f is a function of x and y, or x, y, z in 3D, we need two terms. We have fx dx plus fy dy, and this, of course, is just gradient f times dr. So that means that the integral of gradient f dot dr, it's really just the integral of df. And moreover, this curve C, you could also think about it in this gradient case, you could think of it as going from A to B in the vector sense. But this is not, I wouldn't use this notation. But this is a nice way to think about it. Okay, so it's also kind of, I think it's sensible. Because, for example, if we had this integral, x squared dx plus y squared dy, this line integral, it kind of makes sense that we should be able to call this d 1/3 x cubed plus d 1/3 y cubed. And we should be able to just integrate this thing, right? Somehow this should be done. So it turns out, yes, you can take the integral out now, and now you can evaluate it at the endpoints, just like you would in 1D. And so that's what this expression here is saying. It says that you can integrate it in terms of the potential. And this cubic expression is the potential of these integrands. So how do you actually prove this thing? Well, what I would do is, if you have f at the endpoints, where again our curve, I was calling it vector A, but if we parameterize this by a curve, let's call this r at A without a vector, t equals A. And let's call B r at t equals B. No vectors. So that means this is just f of r of t, it's a function of time, evaluated from A to B. And this is just like the right-hand side of the 1D fundamental theorem of calculus, right? Because it's just f from a to b equals f prime of x dx, or t dt. So now we just use the 1D fundamental theorem. And so now we use the chain rule to expand this expression, because df dt, it should be something like df dx times dx dt. And of course in 3D, this is the 1D. So if we're in 3D, this should be the gradient of f times dr dt. So if we plug this in, we get the gradient of f times dr dt times dt. Of course, these things, you have the nice cancellation. And so now you replace these t's with just your curve. And really, you can interpret this expression as just the integral of df over that curve. Okay, so I think it's just worth noting that this actually has a nice geometrical interpretation. So let's just say we have a level curve contour map. So, and let's say that this contour is f equals 5, this was f equals 10, and this is f equals 15. So as you move up the contours, you're increasing your f. For example, x squared plus y squared over 2 would have contours looking like concentric circles. So what this theorem says is if I start on this curve here, and I take any curve, any weird curve, and I end on this contour here, then this says that the integral over the curve is actually equal to 15 minus 5. So we've increased f by 10. So that's pretty surprising, because you notice it does not depend on the curve. It only matters how tall, how much we increased f. Okay? And there's one caveat to this. The domain of R should have no holes. So for example, this is okay, but this is not okay. And really what this means, the mathematical jargon, is that this just says it is simply connected. The domain is simply connected. But this is not, this is just terminology. That just remember that if there's a hole or a point missing, then the fundamental theorem of calculus for 3D may not be valid. Okay, but I think in most cases the situation doesn't arise. The one instance you might see this is if you look at the angle theta, which I'm just going to call here arctan of y over x. So remember this angle, it increases by 2 pi as we go around the origin. Right? So if we took a path from here to here above the axis, and we took a path from here to here, we will not get the same value. Right? Because we've actually decreased So we've increased theta by pi, and now we've decreased theta by pi as we've moved along this curve, because the directions are different. And the reason, so the mathematical reason, is that the origin is not defined for theta, right? Because remember, it's arctangent of y divided by x, and in fact, theta is actually not continuous either. So that's probably a bigger problem. But in most other cases, as long as you don't have bad functions like this, you shouldn't have any difficulties with applying the fundamental theorem of calculus in 3D. So I hope this was useful. It turns out this is a very helpful tool to evaluate line integrals, as we'll see later. Thanks for watching.